Thank you. Yes, I'm here today to talk about locks on the wire, with the word locks, I guess, being sort of liberally applied. I'm me. You might know me from previous BSides Canberra hits, such as Oh My God, There's a Fire and The Power of Slash. Disclaimer before we start, really just talking about actually network-based, we call it attacks, functionality of these things. So not the typical red team pen testing approach, although you might use it alongside those. You might say, well, how do I get network-based access to a lock? Few ways that you could do that. Publicly accessible network points, such as in the lobby, that happens to be bridged onto the right network. Wi-Fi tends to extend outside of the building. Perhaps you are doing a red team and you've dropped an implant. You might be able to pull a power over Ethernet device off the wall. And a lot of these things have 4G, 5G, whatever, mobile backup. So you might even find them through war dialing. Should probably also put on, there is quite often an option where the vendor will have a internet managed tunnel implementation, but those tend to be very vendor specific. So with that out of the way, let's talk about locks on the wire. And what better way to talk about locks and networks than through a modern love story, or perhaps I should say a modern take on a love story. Some of you might have heard of this love story before. There's two big families, Montague, Capulet. They have children, Romeo and Juliet. And I suppose since it's a modern love story and we don't really want to emphasize gender stereotypes in InfoSec, we'll just say Romeo might be a she, her, and Juliet will be a they, them. And then that way we're not pandering to the patriarchy. All right, so being a modern love story, they met on Roblox dating. They quite quickly hit it off and moved into, sharing memes. And perhaps the memes were a little one-sided. So Romeo feels that perhaps she needs to really show her love. And what better way to do that than to hand over an NFT of a jacket? The only question is, how do you give someone an NFT of a jacket? Turns out that Juliet's family is having a major masquerade ball, and so what better opportunity than to use the cover of Masquerade Ball to gift the NFT. So Romeo comes up with a plan. She's going to get car park access, and then from the car park into the building. I'm going to find Juliet's locker in the building because, of course, she has a locker. They have a locker. And then plant the NFT. Something should happen, and then, of course, Juliet will fall in love. Seems like a sane plan for any person. Which, of course, brings us to the interesting part, what we will call the NFT not a heist. Act 1, gain access to the car park or garage. In this case, there's a garage controller on the wall. And perhaps I'm sort of breaking my first rule of this is network access, but it comes full circle, trust me. Right there is the device that operates the garage door and the boom gates. And if you open that grey box, you'll find, of course, enterprise-grade hardware. It's a Raspberry Pi with a relay shield. The other things that are in that box is a SD card inside the Raspberry Pi. There's Ethernet for network-based stuff, and USB power to keep it going. So, of course, as an enterprising hacker, we might pull the SD card and have a look on there. And, of course, we have OpenVPN config, Slack tokens, Google Cloud Auth, application source code, Wi-Fi was disabled, but it did have a standardized Wi-Fi password, which you would have easily been able to access. And of course, the red teamer here goes, well, in addition to this, you could just add some extra code and use this as an implant on the network, which, you know, with Wi-Fi access clearly extending just outside the door of the garage is probably quite handy. But we're talking about the locks, not the red team. So let's look at the application source code here. Everybody loves a bit of TypeScript or JavaScript compiled to TypeScript. The bits in this wall of text that we care about is that there's a post operation for open, and it takes a query parameter relay number that contains a number. This in turn calls a function called handle open gate. And it checks if the relay number is 1 or 2, because there were 2 relays on that relay shield. And then basically just triggers the relay with the number. There is no auth, there is no anything other than a post request with a query string. So when we run this basic curl command to the host on the right port with /access/open relay number equals 1, we're able to take this boom gate from a closed position to an open position. And of course, the hero of our story is in the car park. All right? So the first step of a plan is a success. Now we need to get into the actual building. So let's talk about intercoms. You know, handy little things that sit on the wall, often publicly accessible. This might be the intercom installed in this imaginary building. It has power over Ethernet. It can do video calls, it can do phone calls, and it can unlock the door through PIN codes. It can do other stuff too, but let's stick with this for now. How do you find one of these on the network? Well, they respond to UDP broadcast. And they'll hand back information such as the IP address, the serial number, what type of device it is, what version of software it's running. You can also do some other stuff through this interface. But also, if you just go to the IP, you'll see that they have a handy web interface. But it is, of course, protected by username and password. So you can't do anything with it, of course. So we put the web interface aside, and let's have a look at the network traffic. In general, everything in this talk can be done with Wireshark or DNSpy. It's not super difficult. And we see that the broadcast device identifier protocol is running on UDP broadcast port 8002. And it sends a HIP 1.0 request :echo. It's sort of HTTP-like protocol, but it's not. And the response, as we can see, the stuff that we saw on the screen. So the serial number, the MAC address. I don't think we saw the MAC address, but it's there. Software version, variant name, the ports where the web server runs, etc. Also observe that there's a very similar protocol running on port 8004 that contains a bit more information. So it discusses things like the video information, SIP. You can see if a door is configured, and it also has some encrypted packets. I have no idea what those do, so if someone's looking for a research project, I'm sure there's some interesting stuff there. But one packet I did notice, which is this concept of remote config. So when you go in and you find something on broadcast, you might need to reconfigure it because perhaps the IP address or whatever isn't set up correctly. And so you can send this packet that does request xconfig. So anything that's a request is a client-side request. It's not the device responding. And it has some stuff like DHCP enabled, IP address and net mask so that you can remotely configure the device. In order to send this packet, you have to enter an admin password in the UI. And then I noticed that there is a very interesting line there which says auth. And I thought, well, that's sort of interesting. You have to enter a password and there's an auth header. I wonder what that could be. So let's go dig through the source code. I call it checksum because I guess that's sort of what it is. And we'll see that there's a function here called sendConfig. I don't know if you can read this at the back. It's not really all that interesting, but the function sendConfig has a bunch of headers. It adds a request, sequence, MAC address, DHCP-enabled IP address, netmask, default gateway. That sounds exactly like the packet that we saw. And then the bottom here, there's a bit of a base64 hashy thing. That seems somewhat related as well. And then the last line is to add that base64 hashy thing back into the message. So if we take the time to read this, we see that the first thing it does is it hashes the password as a SHA-1, just raw SHA-1, converts that to a base64 string. Then it adds that string plus a challenge token, which incidentally is always an empty string. I think they wanted this to be a little bit more advanced, but never got around to it. And then the entirety of the message, which is the packet, as a single string. And then it computes a new SHA-1, that is the concatenation of the base64 of the hash of the password, plus the message. As it happens to be, we have the whole message, and we have the auth, or the checksum challenge. So if you put this together, you can brute force the password. So let's see how that would work. Right. So we take this packet here, and then we put that into our cracker. Why are you not showing on screen? Yep, I might just restart that. Close window, start it again. All right, there we go. And then we can type in some words. So we know from reading the documentation that the default password for this device is 2N. So a 2-character default admin password that's very secure. Can't brute force those things. Let's try in a few others. Admin, password, and let's try to crack it. That didn't work. Now I happen to know what the password is. I mean, you could brute force this, or you could certainly run a much larger word list than my 4 words here. And we can see that the password has been cracked as demo. There is a little bit more to it than this when you're doing it. You got to realize that the auth header gets added after it sums up the message. So basically, when you're brute forcing, you only take the first couple of lines. Any line that occurs including auth or after auth, you discard. But this should eventually make it onto my GitHub, so you can do that. Right, so now that we know what the admin password is, we can go ahead and log in. All right, great news. You are now within the network. I should mention that if you're standing outside the building, yes, you can pull that device off, and you can just sort of plug in because it's broadcast. It works. All right, but getting into the intercom doesn't get us into the building. So why did we take this detour? Well, that takes us to the next act, which we talk about door controllers. So similarly to the garage controller, there's another gray box here. This one's bigger and fancier and more corporate. This is an integrity door controller. They have this nice interface where you can just manage the integrity system with GET requests, because then you can just make a static HTML page as the control panel. So from their documentation, because I didn't get the chance to actually mess with the integrity door controllers, apparently those things are not welcome targets for pen tests. You can lock a door with a URL like that. It basically says the door number D1 on controller 3 with the action lock. So that locks the door. Similarly, you can do other things like disarm the alarm, turn off the master caution indicator, bunch of stuff. Their API documentation is, I would say, deliberately very lacking. And if you want to get the SOAP files or the Postman files to actually see what all of it does, there's a whole bunch of NDAs and legal stuff, and so sharing any information that you have from integrity might, you might want to be cautious with it. But of course, I am not a lawyer, and even if I was, I'm not your lawyer. So take that as you wish. But once we're logged into the intercom, you can poke around in some services, and we'll see here that we have a HTTP command setting. And there's a URL configured with the icon of a door and a username and a password, but we can't see where that password is. Except if you just look at either the developer toolbar, or you go into Burp and you see the API JSON response that loads the content into the page, you'll see that the plaintext password is right there. You could also export the config for the device and crack the raw SHA-1 hash that it has stored for the passwords. All passwords on the devices appear to be SHA-1 in the config when you just export that. So now that we have this password, well, let's go back and think about this. So we have a door lock that we can control through a GET request, but the documentation only describes the lock action. It doesn't describe any other actions, probably to make it really hard for people to understand how to unlock the door. You might think that, hey, I'll just change lock to unlock and do a curl request. But I did do some reverse engineering of some of their other tools. So they have a few public Android apps. So you take a look at the APKs, and you'll see that they generally would probably use the command toggle or open rather than unlock. But like I said, I didn't get a chance to test this on a real integrity system. And you'd need to know what controller and what address the door that you want to unlock is. So this is kind of not good. I mean, it could work in a pinch. Luckily, there's a much simpler solution. You add a user and you just set door access true, and then a badge number, and then Romeo, she can just wander through that door. Easy. All right. So now we're on stage 3. We got to get into the locker, which takes us to Act 4. Smart lockers. I guess most modern buildings with hot desking and hybrid workforce or whatever, these things they'll either be in your office, or they'll probably be on the way into an office soon. These systems are made up of many parts. There's the individual locks inside the locker, which is the exhibit 1, I guess you would call it. There's some hardware plates, whatever. Then there's item number 4, which is the lock controller. That tends to sit underneath all of the lockers, so you can just unscrew the kickboard and get to it. It speaks to the lock. I'm assuming something like IC squared. I don't really know. And it speaks serial RS484, if I remember correctly, to the item that's circled, which is the main controller. So this controller sits on the network, and it has daisy chains of the other controllers up to 256 locks per controller, and then you need another controller. So usually there's quite a few of these controllers around the building. You can probably do a whole bunch of other attacks, like serial or IC squared direct communications to the lock, but I, again, looked at TCP stuff. How do you find these? Well, guess what? They respond to UDP broadcast, just like everything else. And, like everything else, the discovery tool has a bunch of other interesting information, like configure the IP, reboot the device. I didn't look at those. Probably, again, a whole bunch of other stuff that you can do that's super interesting. I think each one of these devices, so if I could probably have been their own 1-hour talk. But I did what I did in the time I had, so here we are. So again, I looked at the TCP protocol. And between the management software for the lockers, which is either like a .NET Smart thick client or a web-based client, you'd see this on the wire. And it looks suspiciously like some sort of plain text protocol, which is always great. And it's all sort of readable. There doesn't appear to be anything really suggesting encryption. There's no usernames and passwords, except this little bit at the start, which has authentication, but it's just a bunch of hex codes. So how do you actually know what this thing does? Well, we go into DNSpy, we load up the scanners and whatever we find, the bit of reference code for the grauth-A packet, because that was the first packet we saw. We see that generates a new authentication A request. As anything else in .NET's DNSpy, you just follow down, you analyze, find reference, analyze, find reference, you work your way down, we find something called GAT NetWriter. So this is something that communicates over network through a GAT writer communication. It takes some arguments, which is a server, a port, authentication password. Well, that's pretty handy. Let's analyze a bit further and see where this thing gets called from. Well, it turns out there's something called an IG7 communication. Unfortunately, they have so many different device frameworks and communications, but however, we ended up here. And we see that it has a wrapper that takes communication channels, presumably that's the TCP socket to IP port, and a 3-letter thing called GAT. Okay. So let's go back to this and we go, okay, well, it appears that the password is GAT, but we've got to dig a bit further. And I'll spare you all of the endless screenshots of code, but we'll summarize it instead. This is how the protocol works. We send a request, authentication A. The server responds with the auth A result containing a random A and a string of hex. We decrypt this using AES, EBC, and the password GAT. Again, strong passwords, hard to break. That decrypts into this hex string, and it's essentially just a bunch of random bytes. The first 8 are filled in, the remainder 8 are zeros. Then what the client does is it fills up those remaining 8. It encrypts it back to AES with the password GAT, and then sends this as the auth B request with the hexadecimal of the encrypted string. And then you get the result state 0, which means you are now authenticated to the device. You can add master keys, unlock any locker, do whatever you want. This is essentially the only auth. There is one other thing of note, and that is that the final filled in full 16-byte random byte value is set as the session key. But I never observed the session key being used for anything else. Presumably it is used to sign things like a firmware update, but yeah, all you really need is this bit. So again, do a demo. I have the protocol here, and we can see we get the random A input, and again it's off screen. I'll just launch it again. And so if we take the encrypted string, we decrypt it, we get a bunch of zeros. We'll just, oops, no. 1, 2, 3, 4. We'll encrypt those. No. Of course, I had the wrong number of bytes. We'll encrypt those again. And I don't even know if the protocol verifies that the first 8 bytes are the same bytes that it's set. Chances are you could just send it a pre-computed string and then that becomes the session string. But the one thing we can see here, if we look now, so this was the first random bytes we got back from the server. We decoded, we changed it to 1122, but if I instead take the final result from the PCAP, you'll see that when I decrypt this, the first 8 bytes stays the same, but the remaining 8 bytes is different. So even if you didn't know what this was, I suppose you could just grab the second value, decrypt it, and reuse the existing session key. Right. So now that we can authenticate to the locker controller, we can send the generic grgetLockerInfo command. That will give us the inventory of all the lockers available on that controller. In this case, we found that locker number 700 is the one that we're interested in. We query its state, and we can see a bunch of values. Essentially says that it's locked, and it's this type of model, and some dates. We clear the auth list. We set a locker action to toggle the locker state. It changes state, and then we action that. And now that locker is open. Great. We only have a few more steps in our process. So the first thing we got to do is we got to plant the NFT in the locker, and then we got to lock the locker so that it's a secret and a surprise, right? Luckily for us, toggling the state of the locker from locked to open, we can just replay and toggle it back to locked. So that's that. Nice and simple. Now there's that bonus step. We don't really know what's going to happen with Romeo and Juliet, but instead I'll talk about Gartner some more, because they don't just do lockers, they also do doors and other stuff. So I dug through some of the other DLLs, and we found that there's a door controller communication. Very similar, rather than communications channel, in this case it explicitly calls out the TCP client, and we can see that the password again is GAT. However, we'll also, I don't know if you can have sharp enough eyes, you'll see that there is a chance that instead of the password being GAT, it defaults to DC 7200. I don't know why, but I think it tries that one first, and if that doesn't fail, it falls back to GAT, and if that doesn't work, it does something else. I didn't have any doors to test this on, so I don't have any PCAPs, but I guess we can show that one of the reasons why this is so interesting is, well, you can do stuff like update the firmware from the functions. We can see at sort of the top of this, we have update firmware request. And then as we look sort of further down on the door control communication, there's a whole bunch of like fire control for allowing fire access on the doors, which is why it might be a really bad idea to just go throwing packets at this in the real world. You don't want to turn your building into a death trap. So use this with caution. Right. And of course, while we were busy talking about doors, love has happened. And I realize I'm running a little ahead of time here, but maybe we can all have a bit of a longer lunch. So conclusion. Security solutions continue to have bad security. I think that's something we're seeing more and more recently. IoT security, which is, I guess, what these things are, they tend to be another 20 years behind your VPN endpoints and firewalls. And particularly, as far as I've seen in this space, they tend to rely quite heavily on secrecy and/or litigation to keep this information from becoming public, hence staying secure. And that is actually it. Any questions from the audience?
A round of applause for Eldar. That's good. Are there any questions in the audience? We have Josh and Antoinette. They'll run the mic out if anyone has any questions. Plenty of time. It's a bit hard to see, so wave your hand around.
There's one all the way at the back there in the yellow shirt.
Good, good. Antoinette's running.
Hey, thanks, Eldar. Did you have to deal with the vendors, and were there any issues with them threatening litigation?
So the simple answer to that is I've dealt with one of the vendors. They were okay. The other ones, I guess you can consider ODA.
Any other questions? Wave like crazy? Okay. All right, that's probably
Okay.
really good.
Thank you.
Another round of applause for Eldar.